Okay, welcome back. Right now we're going to talk about we're going to change things up a little bit, right? We've already talked about yesterday we discussed mainly nucleophiles. We discussed the SN1 and the SN2 mechanism, substitution mechanism, and we discussed basically, what is a nucleophile. Oops. So what is a nucleophile? We had the two rules is that it must have the lone pair of electrons, and two is that the ions or the conjugate bases were better nucleophiles than their conjugate acids or uncharged species. So ions or conjugate bases of the acid are typically better. Um, so today what we're going to do is we're going to change from nucleophiles, and we're going to change it over. We're going to change it to, I'll change it to blue right down here. We're going to change to electrophiles. So we will be doing some question answering sessions on this. So don't worry about that too much. I'll release those later on this week. So we're talking today about electrophiles. So what an electrophile is, right? A nucleophile wanted a nucleus. So if we write that, nucleophile, they wanted nuclei, and nuclei are positively charged. So they're attracted to positively charged nuclei. So nucleophiles, phile loves nuclei. So basically, it loves the nucleus. So it must have basically a negative charge or be willing to donate the lone pair to form that dative bond with the nucleus. Electrophiles are the opposite, right? Electrophiles, they can be positively charged species, and they withdraw. They withdraw electrons. So all those nucleuses that we saw in the previous questions, those are considered electrophiles, right? Uh, we talked about the stable carbocation. We talked about, you know, a tertiary carbon. We talked about the carbocation. It has what we need. A positive charge and withdraws. It likes to absorb, or it likes to bond with electrons. So that's why when we had those, hydroxide groups coming in, they can come in and attack very easily. They can come in and attack that electrophile. He wants electrons. This is the nucleophile. So it's kind of just like if you imagine it, it's just like your Lewis acid-base theory. Is that your Lewis base is an electron donor and your Lewis acid is an electron acceptor. So electrophiles can basically be characterized as Lewis acids, and nucleophiles can be Lewis bases. So if you did very well on that unit, you can use that unit to help your understanding with this unit. So electrophiles can be positively charged, and they withdraw electrons. So examples of these will be our nitronium ion, which we're going to see how to make these later on in one of the next videos, because it's one of the reaction mechanisms that I feel you could be tested. Nitronium ion, which is NO2 positive. And then we have our methyl cation. So like methane, but a cation. So we've got CH3 positive. So they're very, very good electrophiles. They're very good at pulling electrons away. And what we're going to see soon is that we're going to see that halogens can also act as electrophiles, as well as hydrogen halides. So something like HBr, HCl, HF. So these are hydrogen halides. These are halogens. But then we also have interhalogens. halogens that can work as very good electrophiles, and interhalogens are just a mixture between halogens. ClBr, ClF, ICl. So the mixture of two halogens, between halogens, our halogens and our hydrogen halides. So those are three groups that we're going to discuss later on in this lecture. So I'm just going to take off this bottom part, and then we're going to keep going. Or I'll keep writing down here first. Okay. So basically what we need to know is that, for electrophiles, they either have a positive charge, so either are positive. Ooh, man. Positively charged. Took me a second. Either they're positively charged, which means that they're an ion, or they have a partial positive charge. And what a partial positive charge means is that it's bonded to some sort of electron withdrawing group. So in this case, we've got two ions up here, but we can also look at like HBr, right, or ClBr. In HBr, Br is more electronegative than H, so Br has a partial negative charge, and the H has a partial positive charge. So the H can act like an electrophile. We have the same thing here. We have differences here, and we're going to see that there's, again, there's always some sort of exceptions. We're going to have exceptions up here, and this is basically just based on those basically temporary dipole moments. So it's just where, these are non-polar, but every now and then they can develop a temporary dipole, and we could talk about that a little bit. We'll talk about that once we go through their actual reactions. So good electrophiles are typically positively charged, or they have a partial positive charge, and we can make, non-polar molecules also have partial positive charges every now and then, just based off of those London dispersion forces that we talked about in one of the previous units. So what do electrophiles need, right? They withdraw electrons, so they want electrons. They really want electrons. So let's look at, what might have a lot of electrons, or what we need to know has a lot of electrons, right? So what we need to know is that alkenes, because we're just doing addition reactions in this case, in our unit, so we don't need to know much more above alkenes, but that alkenes are electron rich. They've got a lot of electron density. When we take our draw our overlapping atomic orbitals, right? We've got an overlapping sigma bond, a direct overlap. So we've got a direct overlap right here. But then from the p orbitals, we've also got, let me try to erase this. I'll draw it a little bit better, just because we know it's sp hybridized too, so I'll draw it a little bit different. Carbon. Let's see how I can do this. A small one over here, a large one over here, and carbon. This is our bonding molecular orbital, and this is forming our sigma bond. So that's one of our sp hybrid orbitals. Then we had our p orbitals, and our p orbitals existed above and below, right? And we said that pi bonding was the sideways sharing. So basically, these p orbitals will have our one bonding and our one anti-bonding. These p orbitals interact sideways. They interact over basically this space above above and below the carbon atom. And this is going to be our double bond. So you can see, right, we're going to have electron density not only existing here, the direct overlap, like we said in the 1 unit, sigma bonds are stronger than pi bonds. So these are the weaker bonds. These are, electron rich. They're existing above or below the plane. And pi bonds are weaker than sigma bonds. So we can cause these bonds to react, to undergo some sort of addition reaction. So a way to, another way of explaining that though too, is let me kind of, I'll erase down here. I want to keep that picture up there for now. So another way of explaining this too is that, right, these carbons are sp2 hybridized. So they're sp2 hybridized. They got the open p orbital. And sp2 hybridization, right, if you remember the unit, this is trigonal planar. So it's a trigonal planar molecule. So if we were to draw that out, I'll draw out like a side profile. We've got the carbon. Here's his sigma bond. This is only the sigma to another carbon. Then we've got our hydrogens coming out right here. A hydrogen going back right here. A hydrogen coming out right here. And a hydrogen going back right here. And we're going to see why that is in a second, right? So we've got these p orbitals that are sticking up above and below the carbon, and above and below the carbon, and they're bonded here. So right, we talk about geometry based off of electron or repulsion of the molecular orbitals, and that's exactly what we have here. We've got this big space above and below that's full of electrons now. It's full of this pi bond. It's full of this pi bond, so these want to repel as much as they can, and this is their optimal position for repulsion. But then also, right, the sigma bond is contained between these two nuclei. It's contained. This above and below the axes allows for something that's really electronegative, something that's not electronegative, something that's positive. So let's say our HBr even. These electrons can form and cause a bond between the partially positive hydrogen, and then the partially negative bromine can attack the other side. So the positive charge can withdraw electrons from here so that the negative charge can attack the back side, and that's what we're going to be seeing. Let me just erase this really quickly, and then we'll continue. But basically what you need to know here is that those, geometry does affect reactivity. If you imagine, right, we said steric interaction. Steric was the word. Steric interactions or steric hindrance. So what that means is that there are some molecules in the way. There's some atoms in the way that are stopping anything from coming in here and taking away these electrons. But in this case, we have nothing, right? We've got small atoms on the outside, very repelled by this. So we've got this open thing ready to give away its electrons as easily as it could. So what we're going to be looking at is addition to these. Addition to these is there's no steric hindrance, so there's no bigger molecules in the way, right? If we start to add, if we take away this hydrogen and add a CH3 and add another CH3 here, add CH3 over here, we're going to start to sterically hinder this bond. So this addition is going to occur a lot slower. But with just typical alkanes, which is all we need to know about, maybe single chain alkanes, but we just need to know that it's added because there's low steric hindrance. There's not much protecting those pi electrons from being attacked. So steric hindrance, that's a good word to keep in mind. So we're going to be looking over a few different types of addition reactions to these alkanes. So I'm going to do a few examples, and you remember you need to keep in mind the SN1 and the SN2 mechanisms. So we need to know what forms. This is the very, very important question for these addition reactions. I'm just going to write this down here because I feel it's very important. For addition reactions, you must remember the rules for SN1 reactions. So we must remember that tertiary is more stable than secondary, which is more stable than primary carbocations. And this, I cannot say how important this is to remember for these reactions. It's extremely, extremely important. Tertiary is more stable than secondary. If you read in your book, it's called Markovnikov's rule. So I'd recommend you read that in your book, or you Google it, and you could do a little bit further reading for the most stable carbocations. But since we've already introduced that, I'm not going to go directly into Markovnikov's rule. I'm going to leave that up to you guys. So basically, right, the rule states that tertiary carbocations are more stable than secondary, is more stable than primary. So let's get into. Actually, I'll make another video for the reactivity and the addition reactions. I'll break this up into two different videos. So watch the next one, and we're going to look at what effect the stability of this carbocations has on addition reactions to alkenes. Okay, so join for the next video. See you then.